Hello, my name is Rob Reynolds. Welcome to Business Calculus, Chapter 3, Section 5. And today, since you're business calculus, you're always asking the question, when am I ever going to use this? And this may be closer to an example of where you're going to use this that you're going to get. So business economic applications is the topic. And one of the topics besides optimization, where you take, find the derivative and set it equal to 0 to find maxes and mins, and we're going to continue doing optimization problems. But a new topic that you are all familiar with, hopefully in economics class, is elastic and inelastic, and what that means. So if a quantity demand changes a lot in price, changes a little, a product is said to be elastic. And the most famous example of relatively inelastic, when things are not, right, the demand for gasoline, what's happening? As the price of gasoline increases, the quantity of demand doesn't really decrease because people need gas. It doesn't matter the cost. They're still going to drive to work. And so that doesn't have a strong relationship between supply and demand. So we say that's inelastic. So again, we're going to look at optimization problems, this elasticity concept. And again, when we talk about optimization, what we're trying to do is find out the separation. Oftentimes, if we have the cost is high and the revenue is low, then that's maximum loss, and vice versa. If the cost is low but the revenue is high, that's going to be a maximum profit. So again, notice that these happen at max and the maximums and minimums of the function, and that's why we're finding the derivative and using the first derivative test to find maxes and mins. Or now we can use the second derivative test, which I think I will try as well. So our very first example, we're given the revenue. We're going to find the derivative of this. So 3x squared plus 900x plus 52,500. Set this thing equal to 0. Maybe by factoring out a -3 would be the easiest. And then finding factors that differ and add up to the middle term, setting these things equal to 0, and you get 350 and x to be equal -50, which really is outside the domain. If that doesn't really make sense for x to be a negative value, so you that's called an extraneous solution, and you're going to throw that value out. If you were to graph it, yes, that would be easy. You just graph the function, guess left, guess right, guess on your graphing calculator. If you don't know how to do that, then that's a great checking mechanism. You're just really literally finding the maximum value of the function. You're going to have to change your window, of course, to see that, because your little 10 by 10 window, if you hit zoom 6, is going to be, you're not going to see much of the graph, if any, at all. But you can certainly play around with the window. Zoom 0 sometimes gives you a fitting screen, or at least that'll help you get to a fitting screen. So you can check, but I'm more interested in the calculus than I am the calculator. So again, here's the worked out solutions, and then don't forget about that domain restriction when we're talking about what's feasible for x to be. And x has to stay between 0 and 546. And again, why 546? Because if it goes beyond that 546, then we've got negative values here. And if it goes beyond or goes to negative numbers, then we're going to have negative numbers down here. So we have to cut that off. And those are called x-intercepts. And by the way, your calculator will find x-intercepts as well. To find x-intercepts by hand, you just take the original function, not the derivative, the original function, and set it equal to 0. You could factor out an x first, and then hope and pray that you can continue factoring. And you can see there's one x-intercept right there. And I'm not going to factor that, but you can, well, this is, again, the author used derivatives, and they threw out that -50. So there's example number 1. The average cost function is denoted C bar, and that really literally means we just take the cost function and divide through by x. Now remember, you've been given other definitions, and you'll have to memorize these. The revenue was given as XP, and the profit was defined as your revenue minus your costs. And if your revenue is XP, so it's X small p, don't get that confused with capital P. So small p is the price, capital P is the profit, minus the cost is your profit. So big P and little p. So you have other definitions. So today we're going to be talking about average cost. And again, the average cost is found by taking the cost function and dividing through by x. So I'll find the cost function first, 0.04 plus 0.0002x. Then I will go find, to minimize this, the average cost, I'll go find its derivative. Now remember, this guy is really maybe thought better of as a quick little rewrite as 800 times x to the negative first. So when I take the derivative of that, I'll get negative 800 times x to the negative second, which you may think as 800 over x squared, if that makes sense. The derivative of a constant is 0, so I'll throw that out, plus 0.0002, plus 0.0002. So there's the derivative. I'm going to try to set that equal to 0 by adding the fraction 800 over x squared to both sides. Then I'm going to try to multiply both sides by x squared, so I can just get rid of my factors. And then I will take the 800 and divide by, and then lastly take the square root of both sides. So x will equal plus or minus 2,000. And again, I got to think about feasible and what is feasible. One way to talk about feasibility is to just graph the function. Again, if you hit zoom 6, don't be surprised if you don't see much. Zoom 0 might at least try to help you locate some type of the function, but really what's best if you just go to your window. And I know x can't be negative numbers, and I'm just going to change this to a big, I need to see far off to the right, so I'll go 5,000. I'm just guessing. And then the y values, again, the min, I'll just go zeros because I'm in the first quadrant because it's a real world problem. And I really don't know what, I'll just put a 5 in there and I'll change it if I have to. So that failed miserably, so I'll change the 5 to like a 6,000. And finally I can see the graph and the feasible domain. So again, the author's working this out. And we know that x has to be greater than 0. So to find these critical numbers, which is what they're requesting, I just lost. Again, I would probably use a calculator for that. But critical values that we're talking, well, that's a domain restriction. Use the so the critical value here is this plus or minus 2,000. And to check that with your graphing calculator, we're going to use that graph. Let's change this to the average cost function because that's actually what we're trying to evaluate. Let's change this back to maybe a 6. And if I hit trace, to locate that minimum, you can hit second, calculate the number 3. And I'll guess to the left. Remember, that's between 0 and 5,000, so I'll guess 2. Guess to the right, like 3,000. And it's telling me the minimum. Let me try that again. Second, calculate the minimum. Must not have hit something in. Let's do our left guess as 500. There's that line. I don't think I had that before. The right guess will be, I'll do 4,000. And I know the answer is 2,000, so I'll guess 1,000 in between. And you can see it does give me the x value 2,000. And then the y value is interesting too, but I was looking for those x values to be 2,000. So again, setting the derivative equal to 0 will help me find maxes and mins. Example number 3. Sometimes I don't give you the equations, but sometimes they give you 2 points in space. So they say 2,000 units sell for $10. So I'm going to write that as 2,000 units sell for $10. And I'll use this as my x and this is my y. They also say 250 more units, so 2,250 units sell for a price reduction, 25 cents less. In other words, $9.75. So given these 2 points, you could quickly find slope by doing y minus y over x minus x and coming up with slope. And once you have slope and a point, either I could use point A or point B, I can find the equation of the line, so which they did not give me. But again, we could do a little bit of work. Plug in the y value. I'll use this A value. So 10 is equal to the slope, negative 0.001 times 2,000 plus B. And then I just solve for B using a little bit of algebra, and B turns out to be 12. So once I have a nice little equation, I also need to remember that your revenue is XP. I need to know that your price then is this negative 0.0001 plus 12. That's what we just found here using this y-intercept and this slope. And then I'll write the revenue function by distributing that x, 0.0001x squared plus 12x. And then I'll go find the derivative and set it equal to 0 to find the maximum. And I get, let's see, this is I-12. So if I add that over and divide, I'll get 6,000. And so the price, to answer the question, what price, we always have to go back and ask what they're looking for, would be the 12 minus the 0.001 times that 6,000. And that'll give me, I believe, somewhere around $6. So again, you're welcome to look through how the author worked this out. I have PDF worked out solutions posted on Blackboard, and I would encourage you to print off the worksheet, a blank worksheet, and kind of work along with me. Instead of just watching me work these problems, it's always best to kind of just see if you can work the problems out and then maybe just play the video and pause the video. Again, we can check it using our graphing calculator to find the max. Example number 4, we're going to use profit is equal to revenue minus cost function. And remember, revenue is your XP. And so X is always just X, but your P is given right here. So 50 divided by the square root of X minus the cost function, which is also given. So that's 0.5x plus 500, but after I distribute this negative, that becomes a minus 500. So I'll say P is equal to 50 square roots of x minus 0.5x minus 500. And so you may be asking, how did you get this square root of x? So I'll back up. I took x over the square root of x and thought about that as x over x to the 1/2, and then you rewrite the base, which is 2/2 minus 1/2, and that's what gives me x to the 1/2, but then I just wrote that back as the square root of x. So I did a little bit of work to find that square root of x. Hopefully you can do likewise. Let's go find the derivative of that. And when finding the derivative, I might want to think about it as back up in this term, 50x to the 1/2, because that's easier to take the derivative of that. So you can see I'm going to get 25 over, or times x to the negative 1/2, which I'll throw that back in the denominator, minus 0.5. I'll set that equal to 0. So 50 is equal to the square root of x. And I'll square both sides to get 2,500. Then I'll go answer the question, go find me the price. So 50 over the square root of x is 50 over the square root of 2,500, which is 50 divided by 50, which is just $1. All that work for $1. And again, here's the authors who worked out solution, and it looks like they have something similar, $1. So the last thing I kind of want to talk to you about was this price of elasticity, which how we kind of started with. And to determine whether something is elastic or inelastic, we have a formula for this. And of course, when they talk about percent change, we're talking about the slope, and of course that means the derivative. So that's why we're doing dp over dx. So the delta p is this delta is the change in p over change in x. And we're going to say these are very similar and close to each other. They're good approximations, but they're not exact. I actually like these definitions a little bit better down here. The rate of change in demand divided by the rate of change in price it is your x's are your demands, your p's are your price. So you can see the rate of change over the rate of change, and then the rate of change over the derivatives. So we'll explore this. When I'm talking about elastic, inelastic, and unit, unit is when it's perfectly even. So that's, remember, these are the absolute values, and I'll set that equal to 1. So if it's greater than, if this Greek, it's the Greek letter, I'm sure I'm mispronouncing it. It's called eta. I'll pronounce it eta. You can look up how to pronounce it. I don't know. But it looks like an N to me. So if the absolute value of eta is greater than 1, and we're going to define eta as this change in demand over change in price, then we will have some elasticity definitions. So again, you guys as business majors maybe have seen some of these graphs before and some of these types of problems before. If the demand is elastic, then a decrease in price is accompanied by an increase in unit sales sufficient to increase in total revenue. So these are the types of things that you're going to be discussing in your business economics class. Again, I'm just giving you the math application for this. If the demand is inelastic, then a decrease in price is not accompanied by an increase in unit sales sufficient to increase in total revenue. So let's take a look at an example, and then we'll get out of here. Here's a price function for a product, and it says determine the demand, whether the demand is elastic, inelastic, or has that unit elasticity. So I'm just literally going to follow this definition, and I'm going to take the price, divide by x, and then I'm just going to write this as the derivative. But remember, that's the same thing as price divided by x, and then the author is writing this as dp dx, but it's really just the derivative. So the price is given, 24 minus 2 square roots of x divided by x, and then divide all of that by the derivative. So the derivative of this thing is 0. Let's rewrite this first of all. So p is equal to 24 minus 2x to the 1/2. So p prime is 0 minus x to the negative 1/2, which you hopefully will see as negative 1 over the square root of x. So I'm going to write that down here, negative 1 over the square root of x. Next, I'm going to do a little bit of work. I need a little bit more space, so I'm going to use my snipping tools and create a page and edit paste. Should have done that earlier, sorry. All right, so I'm going to try to clean this up just a little bit. This is really 24 minus 2 square roots of x divided by x times the reciprocal, the square root of x over 1, and of course I've got a negative here. So if I start distributing, I'll get negative 24 square roots of x plus 2x over x, which you could write as negative 24 square roots of x over x plus 2, because those x's will get 2x over x I could write. And let's go back. So they say, let's go find the unit elasticity first, because I know that definition. That definition says this must equal 1. So I'm just going to set this, well, it says the absolute value of this has to equal 1. So I'm just going to set this equal to 1 and look for solutions. You could try to do this algebraically. I'm going to cheat and use my calculator by letting the first function be this and let the second function just be 1, and then I'm going to find the intersect. So I'll show you how to do that. If I haven't told you this trick already, I like this. If you have a TI-84 or higher, you can hit second y equals, and it'll set up a nice little fraction, so you don't have to use parentheses. I'll type this in. And then under y sub 2, I'll make it a 1. Since I might have messed around with my window before, I'm going to hit zoom 6. That'll set it back to a standard 10 by 10 by 10 screen. And you can see I need to see further off to the right. So I'm going to go to my window and look much further to the right. I'll just look out to 100. I won't mess around with the y's yet. That looks horrible. I wonder if it's because I forgot to stick this in absolute values, so it's not going negative. So let's see. If I type this in correctly, I'll put this in absolute value. Again, I hit math, num, and then typed in under absolute value. So I think I have this typed in here correctly. I set my window. You can go to 0 to 100, and the y values could be 0 to 5. Whoops. What did I do wrong now? Oh, my min is greater than my max, so 0 to 5. And then when you hit trace, I could calculate the intersect by hitting 5, by identifying the first function, identify the second function just by pressing enter, and then come over here and give me your good guess. You can see 64 is the break-even point, so therefore that's where its unit elasticity, when its x is 64. So my final solutions then, it's elastic for anything that's less than 64, between 0 and 64, and then it's inelastic for anything that's greater, but it doesn't go off to infinity. It'd be from 64 to the x-intercept. So I'd have to find the x-intercept of the original function. And to do that, again, here's some, you can look at Blackboard, but I'll just jump to the, if you graph the original function, you can see right there is an x-intercept, and you can also find that on your graphing calculator as well. And that'll turn out to be the x-intercept of 144, 0. So if you have questions on how to find the x-intercept, but remember, it's not this function. You have to go back, clear out all these functions, and type in your revenue function to find your x-intercept. All right, I hope you found this video helpful. Here are the formulas that you should have memorized for your next test. There will not be a cheat sheet, so you need to know these definitions by heart. If you have any questions, feel free to shoot me an email, and I'll be happy to. It looks like there's a couple other examples in here. Which you're welcome to. It looks like number 33 is another example. Go ahead and try to work that out on your own if you have time. Thanks.